Welcome to Unit 4X. This is for ELTN 132, just a short little unit. And we're going to cover a few topics here. The first thing that we're going to be looking at is what is called SOP and POS, and then DeMorgan's transforms or transformations, and then some applications of how these all work together. So when we think of an OR gate, for example, symbol looks like that. And for example, if we have an input A and B and an output X, we write that formula as X equals A or B. Now this doesn't really represent the addition of these two terms, although there are some similarities. But we do sometimes use this term sum. And the same similar situation with AND gates. If I draw an AND gate here, and an input A, B, and X, we would write here X equals A and B. And remember, sometimes the way this is represented is sometimes we put a little dot there, and that's kind of like multiplication. And so often that is written as a product, even though we're not really multiplying them. And so what we're going to be talking about are what are called SOP, which stands for sum of products, and POS, which stands for product of sums. And I'm going to explain how these two terms, what they really mean. And it's really order of operations. Is the OR gate first in the circuit, or is the AND gate? And you'll see that in just a second here. So a sum of product circuit can be drawn like this. The sum being the OR term here. And I'm going to put a little plus there just so we can kind of keep track of what we mean by sum. And it's a summation of product terms, which, as I just mentioned, are basically AND circuits or AND inputs. So in this case, we have four inputs. We'll be creative and call them A, B, C, and D. And I'm going to put dots here just to represent that those are products. So this is a sum. We're adding essentially two product terms together. Now what I'm going to do is draw out a whole truth table for this. I'm not going to do this live because it would take too long. But what I'm going to do is draw the truth table for this whole circuit. And I'm going to show you real quickly when I do a truth table, there's kind of a fast way to do it. If we start with the D terms and simply alternate 0, 1, 0, 1, 0, 1. Oops, did I make a mistake there? Oh, I think I left off a row. Let me fix that. Okay, there we go. I left off a row. So then for the C term, we can start with 0, 0, 1, 1, and alternate now every other set of 2. We can fill that in. And then for the B column, we're going to go 4 sets. So we're going to go 0, 0, 0, 0, 1, 1, 1, 1, and so on. And finally, for the A column, we're going to do it in 8s, basically. 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 1, 1. So that's just kind of a quick way to fill in the truth table. Now I got to go clean it up. Now remember, the whole purpose of a truth table is to describe all the outputs of X that are true, or actually we're defining whether they're true or false, ones or zeros, for all possible input combinations. And I noticed that some of you in some of your homework didn't write this in this binary counting sequence. Now it's not required that you do that, but it'll make it a lot easier because everything will be then a lot more consistent for us to look at, because that's counting from 0 all the way up to 15 in this case. So let's take a look now at the outputs here. If we take a look at the outputs of A and B, we can see that that is A and B, and the output here is C and D. So rather than go through this whole truth table, we can quickly identify which cases are where X is true. Since this is an OR gate, anytime that both A and B are true, okay, A and B are 1, we know that we'll have a 1 on the output because that will propagate that 1 all the way to the output of the OR gate. So let's take a look at where that's the case. Well, that's going to be these last 4 here, right? Because we have, those are the last 4 here, are where A and B are 1. So I'm going to fill those in there. 1, 2, 3, 4. And the other situation, this is a little trickier because you have to kind of keep an eye out for where they happen, but the same thing for C and D. So the only time we're going to get a 1 on the output that will then propagate to the output of the OR gate, let's say, for example, A and B are not 0, or A and B are not true, so you have a 0 there. We're looking for where both C and D are 1 to have a 1 on the output. So where does that occur? Well, it occurs here, it occurs here, and here. Now there's some redundancies here, and we'll learn a little bit later about how some of those redundancies, for example, this last row here and this row here, we've got some kind of situations where both parts of the circuit provide a 1. Okay, and then so those are the only situations we're going to have a 1, so the rest will fill in with zeros. 0, 0, 0, 0, 0, 0, 0, 0, 0. This marker is a little fat, but you get the idea. So we have a total of 1, 2, 3, 4, 5, 6, 7 situations that will produce a 1 on the output. And interestingly, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 situations where we have a 0 on the output. So this is what is referred to as sum of products. The term, we're basically summing on the right side these product terms on the left. And in a lot of these situations, you're going to see that the truth table is, sometimes there's only one output that's true, but a lot of the times it's going to be a mixed combination of which ones are 1s and 0s. Okay, so the next circuit we're going to look at, in this case, is product of sums. So we've got a product here with our AND gate, and we're having our sums with our ORs here. And in this case, let's take a look at what the outputs will be. So for the intermediate stages, for the outputs of the OR gates, we have on the top A or B, and the bottom we have C or D. Now, what we can identify is where each of those are, but we have to make sure this is no longer an OR gate here, it's an AND gate, which means that both of these conditions have to be true. Before we actually fill in the truth table, we need to kind of think about that for a second. So what I'm going to do is what we basically did last week, where we named these intermediate terms, for example, U and V. And I'm going to modify the truth table so U represents A or B and V represents C or D. Okay, so I've included these intermediate terms, U, which is A or B, and V, which is C or D, and I've added them to the columns like we did last week. So let's start with U. Anytime A or B is true, okay, which would be here, 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 and all the way down. Now, how am I getting that? Whoops. Basically, what I'm doing is, again, looking at any situation where A or B are true. So here B is true, so that'll be a 1. Here for these 4, A is true, so we'll have a 1. And then here both A or B, either of the situations is the case. So let's take a look at V. When are C or D true? Well, you have it here, 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 all of those. And let's take a look at just all the D's, for example. D is a 1 there, so it's copied over there, 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 every other one basically. Sorry, I keep slipping down there. And then we need to look where C is true. So we have C is a 1 there, so we have a 1 there. And I think that is, oh, we got one more C right there. And all the rest of those are going to be zeros. Now, if you notice here, there are a lot more 1s than zeros, right? In fact, in a way, it might be easier to actually identify where the zeros are. That's, remember, with an OR gate, with the truth table, the only time you get a 0 is if both inputs are false or 0. So, for example, for the U term, which is A or B, we can look here on the left and we see that only in those first 4 rows are A or B 0. And all the rest are 1s. So you can almost think of this as like a negative logic situation. There are a lot more ones and zeros, but the zeros kind of pop out a little bit. Same here. Anytime that both C or D are 0, in this case, this case, this case, all 4 of those, or the very first one also, I can't remember if I mentioned that or not, all 4 of those are where the zeros pop up. Okay, so let's finish off the truth table now. So now we're looking at where U and V are where they're ANDed together here. So in this situation, U and V are ANDed where they're both 1s. So we have a 1, 1, 1, 1, 1, 1, and 1, 1, 1. And all the rest of those then are going to be zeros. 0, 0, 0, 0, and 0, and 0 here. Now, these circuits are completely different. They're not the same circuit. What I'm trying to show you, though, is the ways that we sometimes will develop a circuit. It might make more sense to develop it or create it, implement it in hardware as a POS versus an SOP. And in the next section of the lecture, I'll go over that. Okay, so this last section or this next part of this lecture here are what are called DeMorgan transforms. And what DeMorgan transforms are, they're kind of the reason why I explained SOP and POS before this is that the two are kind of related together. DeMorgan was an individual who did a lot of kind of exploratory research with digital logic. He actually knew Boole. At some point, I'll have to kind of dig into the history on that a little bit because those kinds of things are interesting to me. The basic concept with DeMorgan transformation is this. If we have an OR gate here, well, let's make it an OR gate. We can represent that as a negative AND gate. And what I mean by that is we can draw what looks like an AND gate, but put the bubbles on the input, which is, again, basically what we're doing is we're adding 2 inverters to the input. So what I've done is I've changed the logic type from an OR gate to an AND gate, and I've moved the bubble, the inversion, from the output to the input. Now let's see if this makes sense. Okay, so I've drawn out the truth tables for both of these gates. Let's see what the outputs look like. Now for a NOR gate, to me, the easiest way of looking at a NOR gate, because for whatever reason, ORs are very easy for me to visualize, an OR gate would have a true output if any input was true. So the truth table for an OR gate would be 0, 1, 1, 1. But because it's inverted, we're going to take the opposite of that. So in this case, we have a 1 and a 0, 0, 0 here. So the only time with a NOR gate that we have a true output is if both inputs are low. Now let's take a look at our negative AND gate, not a NAND gate because the inputs are inverted. This is a negative AND. Now again, with an AND gate, the only time we have a true output is if both inputs are 1. But in this case, because they're inverted, the only time we're going to have a true output is if both inputs are 0. So again, we'd have a 1 here, and then the rest of these outputs are 0. So you'll see if we compare the two truth tables for X and Y, these two truth tables, they both match. They both produce the same output. And that's essentially what DeMorgan transformations refer to. This going back and forth between the two types of gates. Now, just because it doesn't only work with negative and NOR gates, if we had complemented inputs here, the same thing. If we invert the inputs and outputs, we'd get the same thing. So I'm going to go through a couple examples here of where this pops up in Boolean algebra, and you can start to see the differences between them. Let's start by writing what these the Boolean expressions would be if we're writing this out in Boolean algebra. So basically what this says is X equals A or B not, right? Again, the bar over both terms represents that we have an inverted output. On the bottom, we have Y equals A naught ANDed with B naught. And again, a lot of the time we will not write in that dot to show that it's a product or an AND term. But you'll notice what we've done here is this. We've changed the gate type. So we're going from OR to AND between the gate types. And we're changing the inversion from the output here to the input. Whenever we have those separated bars, that represents that the inputs are inverted. So really that's all there's to De Morgan transforms. But what gets really interesting is that we can actually not only represent these as single inputs, but actual terms that we're trying to convert. And let me give you an example of that. Okay, here I have a circuit that's pretty similar to what we were looking at before with the sum of products, but in this case we've got a bubble on the output. De Morgan only really works with inversion typically when we're looking at these circuits. So here we have A and B, or C and D, but the entire term is complemented. Okay, that's where we see that inverted bubble on the output. Now what's interesting is we can do a De Morgan transformation on this, but what we're going to do is come up with some intermediate terms. I'm going to call, for example, and I'm just going to pick a couple of terms here. We'll use U and V. I'm going to say U equals AB and V equals C and D. And now we can write this equation. What I'm going to do is substitute these intermediate terms into the equation here. So now what we end up with is U or V naught. So all I'm doing is basically doing a substitution here. Now, this, if you look at this, you should think at this point or start to realize, okay, wait a second. I've got an inverted output and it's ORed. I can do a De Morgan transformation on that. So what I'm going to do is write it like this now. I'm going to take U and V, but I'm going to complement the inputs now. So I've gone from OR to and I've gone from the output to the input. Now what we can finally do is resubstitute the A, B, and C, D back into the equation. But this is where you have to be a little bit careful. Let's plug this back into the original equation. So now I've substituted our terms back into the original equation. And what we end up with is this. A and B, and the output is inverted, ANDed with C and D. Now you have to be careful. The bar is not over the whole thing, so it's not one giant NAND gate. Let's see what this circuit looks like if we drew it out. So now this is the equivalent De Morgan transformation of the circuit. Now you might think, wait a second, this is a NOR gate. How is this becoming a negative AND gate? Well, you can look at it two ways. If I took these bubbles, for example, and moved them to the input of the AND gate, and you can do that, there's no problem moving that bubble over, it would look something like this. So I've taken the bubbles from those AND gates and moved them up to the front of the other gate. So it becomes the same circuit. Now, you might wonder at this point, what a pain, why do we even need to do this? Well, take a look at the two different circuits. This circuit on the top requires two different types of gates, AND gates and or NOR gates. But this, we start to use the same, what they call typology of gate. Even though it's NANDs and ANDs, they're similar, and we know that we can convert a NAND to an AND by simply adding an inverter to it. So one of the advantages here with this POS method is that if we can keep all the gates with the same type of gate, that can save us in design costs and component count. So let's take a look at a kind of a more in-depth example here based on the homework from last week. Okay, so hopefully you worked on this homework last week and you'll start to see where this becomes significant. I thank you to one of the students. I'm borrowing basically their work that they turned in because it was really very well done and presented. I appreciate that. So I can use that in this example here. So in this case, we're creating a truth table based on these different gates, NAND, NOR, OR, and a NOT gate. And what was kind of interesting about this circuit is there's only one condition here where you have a true output. All the rest of the outputs are zeros. And when you see a circuit like that, sometimes where it's predominantly zero, that's kind of, you think of that as a negative logic circuit. There are a lot more zeros than ones. And in that case, sometimes it's easier to implement the circuit as a POS as opposed to SOP. Now, this is kind of a weird way to say SOP because these aren't all product terms here, but it is summing it as a kind of an OR gate type output. So this would be viewed as more of an SOP than a POS circuit. Now, so this progression here, the student identified all the different T, U, and V variables to get to the final output here. And again, we only have one case where it's a 1. So what we're going to do is take a look at this 3 different ways. We're going to look at it as a Boolean algebraic expression, and we're going to see if we can convert it into a, using DeMorgan transformations, convert it into a POS expression. And then we're going to look at the truth table, the logic circuit, and see if we can kind of figure out how that works. And then we're going to also look at the truth table and see what we can identify for that one output that might make the circuit a little bit easier. Okay, so now we're going to convert this circuit into a Boolean expression. We're going to say x equals something here. And in this case, we have A and B not. A, B not. And we're going to, it looks like at first we're going to kind of OR, but we'll complement the whole thing. And then we have C or D not. That's that term. But because it's a NOR gate, we're going to have a bar over the whole thing here, like that. Try to clean that up a little bit. Okay, so that is the expression for this circuit. What I'm going to do is go through the process of doing a DeMorgan transformation with this. And to start with, what you want to do is identify some, like try to look at the big picture. We've got a term here that's ORed with a term here, but the whole thing is complemented. So what we're going to start with is using this A and B not term and the C or D not, I should say, term, and do some substitution to find out what the actual DeMorgan transformation will be. Okay, I'm going to identify these other terms here. So we're going to define U as equaling A, B, not. And the reason I'm including the not on there is because it's part of this whole term here. And we're going to say V equals C or D not. Okay, so now we're going to write this in terms of X with a substitution. So we're going to say in this case X equals U, and then we have an OR here. We haven't done any transformation yet. U or V. And if you take a look at what U equals, U is A and B not, and V equals C or D not. So now that is not the final solution because ultimately we still have this bar on the top here. We can't forget that we've got that big bar on the top. But what we're interested in is doing the substitutions back in now and going through the DeMorgan transformation. So if we do the DeMorgan transformation on these terms, we end up having X equals U naught and V naught. All I've done is I've changed the outputs to the inputs, moving the bars to the individual parts here, and I've gone from an OR to an AND term. Now let's go ahead and substitute the original terms back in. We're going to substitute the terms back into U and V. So U is A and B naught. So I'm going to write that as A and B naught. But we also have a bar over it. Remember, U represents A and B naught, but when we complement U, we have a double bar there. And then we're ANDing it with V, which is ANDing it with C or D naught. Okay, in that case, do we have a bar on the top? And the answer is yes, because V, remember, equals C or D naught, but we have a bar over the entire thing there, like that. Now, when you see double bar, if you remember what that represents, basically that's saying we're complementing a complement. A way of looking at it is like this. If you have an inverter connected to an inverter, and we have an input A, for example, here, the output will end up being A. It's complemented twice. So what does that mean? That means that A, B, no longer has any bar over it. It's just A and B. But we're still ANDed with C or D naught in this case, or ANDed with C or D naught, and we have a complement here. Now, are we done yet? And the answer is no. Why? This is where it kind of gets fun. Do we see any further DeMorgan transformations that we can perform? And the answer is yes. This term inside here can also be DeMorganed and converted from an OR gate to an AND gate. So let's go ahead and do that with some substitutions again. Okay, so for our final DeMorgan transformation, we're going from an OR to an AND, and instead of having the bar over the top for the output, we're going to complement the individual inputs here. So what we end up with is C inverted, and then D has two inversions. Now the reason for that, again, is we're going from OR to AND here, and we're splitting the output into inverted inputs. Now again, in this case, D double naught is going to equal what? Those bars go away, and we end up with C naught and D. Now, let's substitute this back into the previous equation. We're not done yet because we have to go back to look at what we had here with A and B. So for our final equation, we're going to have A and B ANDed with C naught and D. That is going to be the final equation. There are no OR terms here. We've done the complete DeMorgan transformation. Okay, we finally got through all of that. So which equation looks simpler here? Well, I think probably if you're looking at it like I am, this bottom equation looks pretty reasonable. And what's interesting now, let's take a look at our truth table here. What's a situation where we have a 1 here on the output? Well, it's A and B and C naught and D, which is what we have here for this equation. So either of these circuits would work fine. What does the bottom circuit look like? Well, let's take a look and see what, if we look at the original equation, let's see if we can derive it the same way, basically doing DeMorgan, but doing it with the gates instead of through Boolean algebra. So here's our original circuit. Well, let's take a look at this NOR gate. Can we convert it to a negative AND gate? And the answer is yes. So all I'm going to do, again, I'm going to change the gate type from an OR to an AND, and I'm going to take the complement from the output and move it to the inputs. So let's redraw that. I'm going to put 2 bubbles here and make this what's called a negative AND gate. Okay? Now, what's interesting is that when you have a bubble and a bubble, they end up canceling. Again, that's like 2 inverters connected together. Okay? So I'm going to get rid of those bubbles and draw it like that. Now, in our equation, what we ended up doing is converting this OR gate, basically, to a DeMorgan also. But you'll notice that there's not an inverted output. So what we have to do to fix that is we're going to convert it to this. We're going to draw it as a negative NAND gate. Okay? So there is a way to do DeMorgan transformation between an OR gate and a negative and create this negative NAND gate. Again, we're converting all the inputs here to negative, and we're changing the gate type. So let me redraw that in this circuit. I'm going to put a bubble here and a bubble here. And this is our NAND gate now. Now again, you'll notice we've got a bubble and a bubble, so those bubbles can cancel. And we have a bubble and a bubble here. So what does that mean? That means that inverter can completely go away. If only it was as easy as erasing it. And what are we left with? We have x equals a and b and c naught and d. So we actually, what we just did there was exactly what we did with the Boolean algebra, except drawing it with gates instead and kind of doing it, kind of using the symbols. And you might think, well, gosh, that was a lot easier. Why can't we just do it that way? Well, the Boolean algebra actually you can create algorithms for it, computer programs that can do this reduction or transformation. And later on, we'll talk a little bit about PLDs or CPLDs, complex logic devices. And the software basically goes through all these processes to do these conversions. Okay, so a lot of information there. Take your time to rewind it if you need to and go over it. I will assign a little bit of homework on DeMorgan transformation and looking at these different types of gate circuits.